Welcome to the Deep Dive. We turn complex research into, well, something you can actually use. Today, we're going deep under the hood of pretty much everything digital. We're talking about data structures.
That's right. Think of them as the architects organizing all that information so it's efficient, fast.
Yeah, because when you search for something online or your GPS finds a route, that speed isn't just raw power, is it? It's how the data is arranged.
Precisely. It's all about the organization. So we're diving into a pretty technical overview today, looking at the core ideas and, crucially, the trade-offs involved.
Right. Our mission here is to pull out the key concepts. We'll compare some basics like arrays and linked lists, and then tackle the really interesting part, advanced search stuff like hashing.
We're basically looking at those fundamental decisions. Do you prioritize speed, or do you prioritize saving memory? You often can't have both perfectly.
Okay, so where do we start? The source material seems to group these things first.
Yeah, it breaks them down into two main families, basically. First, you've got linear structures. Think of data lined up sequentially or right next to each other, arrays, stacks, queues, linked lists. Those are the main ones.
All in a row, kind of.
Pretty much. And then the second family is nonlinear. Here, data is stored more like a hierarchy or maybe across multiple levels. Things like trees and graphs fit here.
And okay, right off the bat, there's a big difference highlighted concerning memory.
A huge one. The sources point out that linear structures, especially arrays, can be pretty inefficient with memory.
How so? Wasted space.
Exactly, because they often demand contiguous blocks. You might allocate space you don't end up using. It just sits there empty. Nonlinear structures, on the other hand, are usually designed to be, let's say, more memory-friendly. They tend to grab only what they need when they need it.
Okay, let's dig into that first category then, the fundamental linear structure, the array. The source used a classroom analogy, which I thought was pretty good.
Yeah, or think of maybe like a row of houses on a street. Each house has a specific address. 100, 101, 102, right next to each other. That's your continuous memory.
And the people living inside are the data elements.
Exactly. And the house number, that 100, 101, 102, that's the index. It starts at 0 usually, so 0, 1, 2, and so on. That index is key.
Because that index gives the array its superpower, random access.
That's a big win. If you know the index, say index 6, you can jump directly to that element instantly. No searching required. Traversal, just scanning through, is also simple. Start at 0, go to 1, 2. Easy.
So incredible speed for retrieval if you know the address. But there's always a catch, right? What are the downsides?
Well, the biggest one is that fixed, static nature. When you create an array, you typically have to say how big it is up front. I need space for 10 elements.
And if you only end up using, say, 5.
Then the other 5 slots are just wasted memory. That's the inefficiency we talked about. And the other major weakness is insertion and deletion.
Ah, right. Especially at the beginning of the array.
Oh, yeah, that's the worst case. Imagine that row of houses again. If you want to tear down the house at index 0, you now have a gap.
And arrays demand that continuity.
Exactly. So you have to shuffle every single house after it, one step to the left to fill the gap. House 1 moves to 0, 2 moves to 1, and so on.
And inserting at the beginning is the same problem, but in reverse. Shifting everything right.
Precisely. If you have 1,000,000 elements, you might have to move almost all of them. That's computationally very expensive. It's what we call an ON operation. The time it takes scales directly with the number of elements, N.
So arrays give us that lightning-fast random access, but they're rigid on size, potentially wasteful, and really slow for adding or removing elements, especially near the start.
That's the trade-off, starkly put.
Which naturally leads us to needing something more flexible, right?
Right.
Something that handles changes better and maybe doesn't waste so much space.
Enter the linked list. It's designed specifically to solve those array problems. It throws away the idea of contiguous memory entirely.
Okay, so how does it keep track of things if they're not lined up?
Through nodes. Think of each piece of data living inside a node, and each node has 2 parts. The actual data and, crucially, a link field.
And the link field is like an address.
Exactly. It's a pointer. It stores the memory address of the next node in the sequence. So the node at memory location 100 might point to a node way over at location 500, which then points to location 230, and so on. They're linked, but not physically adjacent.
Ah, so you only create a node when you actually need to store something.
Right.
No pre-allocation of a giant block.
Correct. Much better memory utilization, generally. And insertion deletion. Super fast.
How so? No shifting.
None at all. To insert, you just create a new node, and then basically rewire two pointers, make the previous node point to the new one, and the new one point to the next one. Deletion is similar. Just adjust the pointer of the node before the one you're removing to skip over it. It's usually an O1 operation, constant time, doesn't matter how long the list is.
Okay, sounds great. More efficient memory, fast changes. What's the downside this time? Because there's always one.
Yeah. The price you pay is losing random access. You can't just jump to element 6 anymore.
Why not?
Because there's no index. The only way to find the 6th element is to start at the very first node, the head, and follow the links. First node, follow its link to the second, follow its link to the third. You have to traverse sequentially.
Ah, okay. So finding element number 1,000,000 means stepping through 999,999 links first.
Potentially, yes. So searching can be slow, ON, in the worst case, just like array insertion deletion was. It's a complete flip of the trade-offs.
And the notes mentioned a variation, the doubly linked list. Just briefly.
Great. A standard linked list node only knows the next node. A doubly linked list node has two pointers, one to the next node and one to the previous node.
So you can go backwards as well as forwards.
Exactly. That makes certain operations, especially deleting a specific node when you're already at that node, much easier because you can easily access the node behind you to update its next pointer. More flexibility, slightly more memory per node for the extra pointer.
Okay, so we have arrays for speed access, but bad modifications.
Yeah.
And linked lists for easy modifications and good memory use, but slow searching.
Yeah.
What if you need really, really fast searching, even with lots of data?
Right. Now we pivot. We're moving from just storing data efficiently to retrieving it at lightning speed. This is where hashing comes in. And it introduces perhaps the most fundamental trade-off we'll discuss.
Which is?
Minimizing time getting that search result almost instantly often requires sacrificing space, sometimes a lot of space.
How does hashing achieve that near-instant search? It sounds almost like magic.
It's not magic, but it is clever. It uses a special structure called a hash table, which is basically an array. But instead of searching sequentially or using a direct index like 0, 1, 2 for the nth, first, second element, we compute the index.
Compute it.
Using a hash function. You take the data you're looking for the key, and you feed it into this function. The function does some quick calculation like a trick. Really, the source called it a jugad, which is a great term for it.
A clever hacker trick.
Exactly, a mathematical trick. And the output of this function is the index in the hash table where that key should be stored.
So the function itself has to be super fast.
Absolutely critical. It needs to be computationally simple, very fast, and ideally it should distribute the keys evenly across the table indices to avoid bunching them up.
And what's a common example of such a function?
The most basic and widely used one is the modulo function. You take the key, k, and you calculate k modulo n, where n is the size of the hash table, written as p mod n meter.
Okay, give me an example.
Sure. Let's say our hash table has 10 slots, so n10, indices 0 through 9. If your key is 10, then $10 is the side 0, so key 10 goes into index 0. If the key is 20, $20 also 0. Key 30 also maps to index 0.
Uh-oh.
See the prop?
Yeah. What if the key is 12? $12 is 2, so key 12 goes to index 2. Okay, but what if the next key is, say, 42? 42 $12 is also 2.
Exactly. That's called a collision. Two different keys hash to the same index. And this is where the real complexity and the different strategies of hashing come into play. The hash function isn't perfect. Collisions are inevitable.
So the effectiveness of hashing really depends on how well you handle these collisions when index 2 is already occupied by key 12 and key 42 wants to go there too.
Precisely. All the techniques that follow are about resolving this collision problem efficiently. The sources break them down into two main approaches: open hashing, also called chaining, and closed hashing, which involves probing.
Okay, let's start with the open hash method, chaining. How does that work?
With chaining, when key 42 collides with key 12 at index 2, you don't try to find another spot inside the main table array. Instead, you start a linked list attached to that index 2 slot.
Ah, so index 2 points to a list that might contain 12, then 42, maybe 52, if that also hashes to 2.
Exactly. The list hangs off the table slot. The table itself stays relatively clean, just holding pointers to the start of these chains.
Seems straightforward. What's the catch?
The catch is if your hash function is poor or you just get unlucky, one of those chains could become very, very long. If index 2 ends up having a chain of hundreds of elements,
Then searching for an element in that chain just turns back into a slow, sequential, linked list search.
right. You've lost the O1, the constant time benefit that hashing promised. It degrades toward ON for that chain.
Okay, so chaining can fail if the chains get too long. What's the alternative? Closed hashing or probing?
Yes. Closed hashing says we stay inside the hash table array. When a collision occurs at index I, we need a strategy to find the next available empty slot within the table itself. This is called probing.
And the simplest way to probe is just check the next spot.
That's linear probing. If index I is full, try y plus del 1. If that's full, try y plus 2 of 2, then 1 plus 33, wrapping around the end of the table if necessary until you find an empty slot.
Simple to understand, but does it work well?
It works, but it leads to a significant problem called primary clustering.
Primary clustering. Sounds like things clumping together.
That's exactly what happens. As collisions fill up adjacent slots off SOLA plus 22, you create these long runs of occupied cells. Now, any new key that hashes anywhere into that occupied run will also have to probe sequentially past the entire cluster to find an empty spot.
So one cluster makes future collisions in their whole area much more likely and much slower to resolve, like a traffic jam spreading.
Perfect analogy. It creates hot spots in the table where performance degrades badly. Insertions and searches get bogged down in those clustered regions.
Okay, linear probing is too simple, causes traffic jams. How do we fix that?
We need to break up those linear runs. The next idea was quadratic probing. Instead of stepping sequentially, +1, +2, +3, you increase the step size quadratically.
Oh, like check 1 plus $1, then 1 plus 4 down, less 9 and a line.
Exactly. You check all plus 12, 2, then all plus 2 and 2 twos, then all else 3, 1, 2, 2, and so on, all modulo n, of course, to stay within the table. These bigger jumps, these long jumps, are much better at scattering collided elements across the table and avoiding those dense linear clusters.
So quadratic probing solves primary clustering. Does it have its own problem?
It does, unfortunately. It introduces something called secondary clustering.
Okay, what's that?
Secondary clustering is more subtle. Imagine two different keys, key A and key B, that happen to hash to the exact same initial index, say index I. With quadratic probing, because the probe sequence, +12, +22, +$32, depends only on the initial index I and the attempt number, 1, 2, 3, both key A and key B will follow the exact same sequence of probe locations.
So even though they're not clustering linearly right next to each other, any keys that initially collide will trace the identical path through the table, potentially colliding with each other repeatedly down that path.
Precisely. It's not as bad as primary clustering, but it still means that slots along that specific quadratic path become more contested, slowing things down for any key that initially hashes to I.
We need to wait for keys that collide initially to follow different paths afterward.
Exactly. We need the probe sequence itself to depend on the key. And that leads us to the most sophisticated technique mentioned in the sources. Double hashing.
Double hashing. Sounds like we use two hash functions.
That's the core idea. You have your primary hash function, 1xGenderK, which gives you the initial index I. But if there's a collision, you use a second independent hash function on h2 to determine the step size for probing.
So instead of stepping by 1 linear or 2, 2, 2 quadratic, the step size is calculated based on the key itself.
Correct. The formula looks something like h2k, h1k plus ih2k, h anno. For each probe attempt, I, 1, 2, 3, you add I times the result of the second hash function, 2, 2, 2.
And since tk $1 gives a different step size for different keys, hopefully, even if key A and key B both initially hash to index I via HDA1, their 282 values will likely be different.
Meaning they will follow completely different probe sequences through the table. Key A might step by 3 each time, while key B steps by 5.
That sounds like it should break up both primary and secondary clustering.
It does. Double hashing is generally considered the best of these probing techniques because it provides the best distribution of keys and minimizes the clustering issues, leading to the most consistently fast search times, assuming you choose two good independent hash functions.
Wow. Okay, that's quite a journey. We went from simple, rigid arrays with fast access but slow changes.
To flexible, memory-efficient linked lists with fast changes but slow sequential access.
And then into the world of hashing, trying to get that near-instant O1 search time back, but facing the complexities of collisions.
Yeah, and navigating those collisions forced this whole evolution of strategies from simple chaining to linear probing with its clustering problems, then quadratic probing's improvement but secondary clusters, and finally double hashing aiming to solve both.
And it all comes back to those fundamental trade-offs, doesn't it?
Yeah.
Especially that time versus space one in hashing. Making things faster often meant using potentially more memory for the table and dealing with these intricate collision strategies.
Absolutely. These aren't just theoretical exercises. The choices made here, linear versus nonlinear. Which hashing strategy to use directly impact how fast your software runs, how much memory it consumes, how efficiently resources are managed. It's the hidden engineering behind so much of our digital experience.
So wrapping this up, we've seen this clear progression, this constant push to optimize and overcome limitations.
We have. And it leaves you with a thought, doesn't it? We saw how optimizing search time with hashing meant accepting complexity and potentially using more space. We started by noting how the memory waste in simple arrays was just an accepted fact for a long time until linked lists offered an alternative.
Right.
So the question for you, the listener, is this. What other seemingly fundamental limits or inefficiencies, maybe things we don't even consciously think about as problems today, like that initial array waste, are we currently just accepting in our technology, waiting for the next structural innovation, the next clever jugad to come along and solve?